So once we combine these two resistors, the next redrawing would look like that. Now in this circuit, what are the only two resistors that you could combine? Parallel R2 and RA. So some RB, it's R2 in parallel with RA. So it's 2.2K in parallel with 3.7K. Now would that mean that you'd use the formula 1 over 2.2K plus 1 over 3.7K and warm up your calculators and give me an answer with 4-place precision? Now, the 4-place precision now, you mean 4 places where if the 5th place is 5 or above, you round up the 4th place. If it's 5 or less, you keep it the same. It's kind of interesting in today's day class, people are computing with the same calculators and they'd always be different by about 0.003. Which means it's the way you set up your calculator most likely where you have a limited number of digits or something. But what did you get here?
1.37.
Is that 4 places?
379.
So it ends up being, when you do proper rounding, 1.380K. Do I need to show the 0 when I have it when it's 1.380K? No, you don't have to have a placeholder. You just want to calculate with 4-place precision. So when rounding up, 1.38K. So then we redraw the circuit. And RB is 1.38K. R1 is 3.3K. It's still 50 volts everywhere.
Yeah.
But not R4.
So we had RA in parallel with R2, combined to be RB, using the parallel formula. Now these two are in series, so we'd simply add them to get our total. And so isn't that 4.68K, is that right? So, any question about that? That's, again, this is kind of review for the final is the way to look at it, and this is important.
Easy.
So,
Gotta find everything.
Yeah,
now we need to find
Current.
I total. Right. We have voltage, we have resistance, we can find I total. It's V total over R total. 50 volts divided by 4.68K. And that's 10.85 milliamps, is that right? Computed on your calculator?
$10.68.
10.68? Now that means that 10.68 milliamps flows here. Can't you transfer that information up to the next redrawing up? And wouldn't it be the same current? It's only one path. Whatever current flows in the equivalent circuit flows in the next redrawing up because you're expanding the equivalent resistor back to the two resistors that you combined in the first place. And how do you expand it back? In series. And current remains the same in all parts of a series circuit, so you write it down. You say I1 is the same as IA. No, IB. Is the same as I total, the same as 10.68 milliamps. So now you know the current flow through each resistor, the resistance of each resistor. You can find the voltage drop across each resistor. You can find V1 and VB. V is equal to I times R in each case, I1 times R1 and IB times RB. So it's the same 10.68 milliamps times each resistor. Top resistor is 3.3K. Bottom resistor is 1.38K. So it's at about 38 volts. What is it approximately?
35.
35? 35 point?
0.257.
So 35.26 volts. I can subtract that from 50 to get the other voltage, because with the voltages have to add up to 50. The voltage drop across RB plus the voltage drop across R1 should add up to 50. So I can subtract 35 from 50, leaving 14.74, right? Or you multiply 1.38K times 10.68 milliamps, you should get the same thing. I do check my math. When I say these things, don't just believe me. People should be punching buttons to check.
Right on.
Okay. And then, what we have here is from here to here, resistor B, we have 14.74 volts. From here to here, we have 35.26. So are we done with this circuit? Yes. So we take what we learned here and transfer it to the next redrawing up. What's the only difference from this circuit to the next one redrawing up? We're taking our equivalent resistor RB and expanding it back to the two resistors that we originally combined to get that RB. When you expand back, there's only two options, series or parallel. In this case, this resistor is expanded back into parallel. And of course, by now, at the end of the semester, you know that the most important law of parallel is voltage remains the same. So we write it down. We say that V2 equals VA equals VB, which equals 14.74 volts. Isn't that simply realizing that when we found the voltage here, it's the same as the voltage here? Now, what about R1? You were done with R1. You can mark it up there. But here we found 14.74 volts, and up here we have, from here, 35.26. Now notice that you wouldn't add 14.74 twice plus this to get up to 50. Isn't this one voltage? Plus this one voltage adds up to 50. Now that we have known voltage, we know the voltage is here. We know V2, we know VA, and we know R2 and RA. We can find the current flow, can't we? So we can find I2, and we can find IA. I is equal to V over R. Put the same subscript, V2 over R2, same subscript, VA over RA. V2 and VA are listed above, so it's 14.74 volts divided by resistor 2 is 2.2K, and it's 14.74 volts divided by 3.7K. So that's around 6 milliamps. What is it? 4 points accuracy, please.
3.984.
Say again.
3.984 milliamps.
That's for IA.
Yeah, that's IA.
Oops, I'm doing some different. Sorry.
6.7 even. And since you had the other one, what is the other one?
3.984 milliamps.
984 milliamps.
That is the right same one.
So again, mark those on our diagrams. I2 and IA. I2 is 6.7. IA 3.98. I1 is the same as I total, 10.68. Now, we're almost done with this course. What you're really getting out of this course is realizing when you see a circuit like this that you know that things like this current plus this current has to add up to that current. That this voltage plus this voltage should add up to that. Those are the kind of things that you really need to see. So we're done with that circuit. We know the current, we know the voltage, resistors were given. Now we take what we learned here and transfer it to the next redrawing. But really what you're doing is saying, what's the only difference between this circuit and the next? Because everything's done except for the one thing that was changing. In other words, you combined to get there, so now you're expanding, and the only one that's expanding is RA. RA is expanded back into what form? Series. So if it expands in series, you know current remains the same. So that's what you would realize, is that RA is the same as R3 and RL. So you expand that back. How did you expand it back? In series, and current remains the same. So you would say that I3 equals IL equals IA equals 3.984 milliamps. That is a realization that the current is the same in this branch, is the same as this branch. All I've done is expanded the arrow. The 3.984 milliamps flows through both resistors. We could also transfer the other information. You know this is 6.7 milliamps. You know this is 10.68. That's the story for current. Now voltage, transfer arrow, we already did this. We know it's 35.26. And we know the voltage across resistor 2, or anywhere along this parallel branch, is 14.74 volts from here to here. And isn't that 14.74 across resistor 2 also? So the only thing we don't know is V3 and VL. You know the I, now you can find the V. V is equal to I times R. Keeping the same subscript. 3.984 milliamps. Okay, so that's an easy one. 984 volts, correct? Million K cancel. Same 2.984 milliamps now times 2.7 K. Or I could subtract 3.984 from the 14.74. So it's around 10. What do you get? So it's equal to what? 10.76 volts. Thank you. So this 14.74 is split amongst these two resistors. In series, voltage splits up. Parallel, it never splits because the fundamental law of parallels, voltage remains the same. So, split it up, V3 is 3.984. From here to here. 10.76. From here to here. So other than power, we have completed this circuit. But now you have a little bit fuller understanding. You know Kirchhoff's law. that I take any loop and kind of estimate if it's correct. In any loop, there's an outside loop, there's this inside loop, there's even a loop here. The sum of the voltages around any closed loop is added, adds up to 0. Or another way of saying that is the source voltage is equal to the voltages around the loop. So if I make an inside loop here, isn't there 14.74 here plus 35.26 here, doesn't add up to 50? If I go in the outside loop, 3.984 plus 10.76 is 14.74 plus 35.26 adds up to 50. So it doesn't matter which loop you take, it'll add up to 0. Even in here, because it's negative positive plus negative positive, and this is negative positive, you'd go negative to positive series 8ing, then it'd be positive to negative. As we went back around, that would add up to 0. And by the way, if you go the outside loop, if you consider signs, this voltage plus this voltage plus this voltage minus this voltage, or the other way around, comes out to 0. It still means the same thing. So the source is the sum of voltages around the loop, or if you include signs, the sum adds up to 0. Kirchhoff described it that way. The sum adds up to 0. Now power is V times I. So do I need to really do that? No, not for Thevenin. So, but you realize to find the power dissipated by each resistor is the current through times voltage across. When you're done with this, don't you know every voltage and every current? So power simply multiplying current times voltage in each case. So you can find the power dissipated by each resistor. Okay, so we're done with our information here. Is there any question on doing this? Because I'm going to erase.
137.
Okay, so,
Yeah, you gotta use that. The x minus 1
Get the
twice.
answer here one more time.
Yeah, and then equals, and then